In part 2, we're going to talk about some more inverses, but we're going to focus on the inverse function. We have a notation for writing an inverse. The notation is called f inverse of x. I know it looks like it says f raised to the negative first power, but that's not how it's read. Because f of x is the notation we use for a function, then f inverse of x is going to be our inverse equation. Warning, f inverse is not necessarily a function. Sometimes we have to restrict the domain in order to make it a function. Remember back when we studied linear equations, we reviewed what was a function and what wasn't a function. We have something called the vertical line test that helps us determine if a graph of an equation is a function or not. Let's consider the function f of x is equal to the square root of x minus 2. This is a new type of function outside of the functions that we've already talked about. We've talked about quadratics, linear, upper level or upper degree polynomials. Now we're going to focus on something called the radical function. So let's first look at what this graph looks like on the calculator. If you put it into y1 equals, you're going to get this graph. What the graph actually looks like is it looks like it's like half a parabola, doesn't it? Well, if you think back to the previous lesson when we did our graph and we found the inverse of y equals x squared minus 1, the inverse equation had a radical in it, and it looked like a sideways parabola. Let's get rid of that. We want to start by finding the domain and range of f. So for the domain, remember the word domain means input or x values. For what x values does this graph exist? Well, some people can just look at the graph and determine it. Like you can see, okay, it starts at looks like it starts at x is 2. And the graph exists as we go this way along the positive x-axis. So the question is, can you plug 2 into the original equation? Well, y is equal to the square root of x minus 2. If I plug in 2 for x, do I get an answer? Well, luckily the square root of 0 is 0, so it works. That means that there'd be a closed circle here as opposed to an open circle, and the graph would go to the right. So we would say x is greater than or equal to 2 because x can be any number greater than or equal to 2. What happens if you try to put in to the equation a number that's less than 2? Well, let's go look at the table for a moment. I want you to notice that anything less than 2 is going to spit out an error message. That's because the graph does not exist there. Hence the reason we say that the domain is x is greater than or equal to 2. How about the range, the outputs? What kind of numbers come out of the square root function when we plug numbers in? Well, let's go back and look at the table here for a second. I want you to look at the y values. Well, we have 0, and then we have 1, and then 1.41, and 1.73. And if you scroll down your table, you'll see that the y values continue to get larger. And again, some people can just look at this graph and know what the range is going to be. Remember, the range are your y values. So the lowest the graph goes is 0. And all the rest of the graph is above the x-axis. Well, the x-axis is when y is 0, so we say the range is y is greater than 0. In part B, we want to determine what the inverse of f is. So if the original function is f of x is equal to the square root of x minus 2, in order to find the inverse, we're going to switch x and y. Remember that f of x is the same thing as y. So we're going to start by flip-flopping x and y, and then we're going to solve this equation for y. Well, we got to get y out from the square root. To get rid of a square root, you have to square both sides. So now I've got x squared is equal to y minus 2. And the only other thing I need to do is add 2. Oops. And this is the equation of the inverse. Now, the next thing we're going to find is the domain and range. But here's the thing. Remember when we looked at the original graph here? Let's get rid of this now. Let's be able to look at what it looks like on the calculator screen. The original graph was a sideways, like half of a parabola. And the domain was x had to be greater than or equal to 2. So that was the domain. And then the range was y had to be greater than or equal to 0. But if you think about this equation we just got, that's a quadratic. And you would think that that's a parabola that opens up and it's been shifted up 2 units. But we had a restriction on our domain and range. So in order to find the domain and range of our new function, I'm going to approach this different from the way the book does it. What I'm going to do is I'm going to go back and I'm going to kind of look at what this the original graph looked like. The original graph went through 2, 0. The next nice ordered pair was 6, 2. And then the next nice ordered pair was at 11, 3. So that's 6, 7, 8, 9, 10, 11, 3. The reason I'm only looking at the nice ordered pairs is because they're easy to flip and regraph. So here were my nice ordered pairs. So we found out that an inverse occurs when you switch those ordered pairs. So the ordered pairs that lie on the inverse are actually 0, 2, 2, 6, and 3, 11. So what's that graph going to look like? Well, here's 0, 2. 2, 3, 4, 5, 6. Here's 2, 6. And then 3, 11 is going to be up here somewhere, 7, 8, 9, 10, 11. I'm probably not doing a great job at drawing this picture, but you get the idea. I want you to think about it. Does it look like the graph of the inverse, the one in red, is a reflection over the line y equal x? Well, it does, absolutely. So, wait a second. The equation of the inverse was a quadratic. It's a parabola. But if I actually graph the inverse, I'm actually only seeing half of that parabola. So because the original function had a restriction on the domain and range, the inverse is also going to have a restriction on the domain and range. In this one, I want you to notice that the domain, the x values, start at 0 and go off in the positive direction. How do I know? Because I find the domain by finding the x value I start with, and then I notice that the graph of it is all off to the right. And then for the range, what's the lowest y value? Well, I want you to notice that the y values start at 2, and the rest of the graph is above that line. So y must be greater than or equal to 2. So also notice that our original domain and range, oh, we're not here. They were on the previous page. And they're already gone. The domain and range of this graph, the domain was x is greater than or equal to 2, and the range was y is greater than or equal to 0. Well, when I did the inverse, didn't those domain and range also flip-flop? Kind of interesting to note. The last question I have is the inverse a function? So, the inverse is the red graph. think about it. If you use the vertical line test through the red graph, does the vertical line only ever pass through one point at any given time? Yes, it does. So the inverse is a function. The inverse is a function. How do I know? By the vertical line test. When we deal with real-world application problems, we don't switch the input and output and then resolve for the output. We just leave the equation as is and just solve for the input. So in the function d equals 4.9 t squared, t is the input and d is the output. This equation represents the distance d in meters that an object falls in t seconds due to the Earth's gravity. Find the inverse of this function. How long in seconds does it take for a cliff diver 24 meters above the water to reach the water below? So, asking me to find the inverse is asking me to solve the equation for t. That's because they asked me then to plug in 24 for the distance so that they could find t. So a lot of times it helps if I actually just go solve that equation for t first. It doesn't really matter. It's the same thing if I do it either of these two ways. I could plug in 24 for d and then solve for t. Or I could first solve the equation for t by dividing by 4.9 and then square rooting this. Because the thing is, I'm going to end up with the same answer no matter if I do it first before I plug it in or I do it after I plug it in. You'll notice that the inverse operations are still the same. So the equation of the inverse is this. This is the equation of the inverse. In other words, it's the equation to find time when I know the distance. So then when I plug in 24 for d and I shove that in my calculator, I find out that the time is approximately 2.2 seconds. A function that is one-to-one, one that has one value in the domain that matches with exactly one value in the range, also has an inverse that is a function. There is another way to show if two functions are inverses of each other by using something called a composition of functions. A composition of functions occurs when you basically plug one equation into the other in place of x and then simplify. This is a little bit different notation from the one that the book uses. The book likes to use this weird notation that looks like this. I don't like it because I don't think people understand what the circle means. I usually like to use these brackets because what it's saying is we're going to plug this equation into this function and see what our output is. We're going to plug this function into x into this function and see what our output is. If we can perform both compositions and both of them equal x, that means everything cancels except for one x, then we say that the two functions are inverses of each other. So let's look at the function f of x is equal to 6 over x minus 2 and start by finding the inverse of this function. Remember, in order to find the inverse, we're going to start by flip-flopping x and y. Since f of x is the same thing as y, we're going to start with y is equal to 6 over x minus 2. Let's flip x and y. X is equal to 6 over y minus 2. In order to get y out of that denominator, what you probably don't recognize is that this is really just a proportion. Remember, if you just have a number or a letter, it really is a fraction. It's over 1. So I'm going to cross multiply, and I'm going to get x times y minus 2 is equal to 6. And then I'm going to divide by x. The reason I divide by x is because this is x times y minus 2. And it's not going to help me if I distribute that x. It's actually going to make more of a problem. So we just get rid of it by dividing. There's only one thing left to do now. To get y by itself, we're going to add 2 to the other side. And this is going to be the equation of our inverse. I don't need to check those equations to find out if they're inverses or not, because I actually went and found the inverse, so it must be the inverse. The last thing that we're going to do is we are going to perform a composition where we plug one number into a function and then plug it into the other function. So we want to find f of f inverse of 2. What this notation means is we're first going to find f inverse of 2. Because think about order of operations. Order of operations always tells us to work inside grouping symbols first. So I'm going to work inside the grouping symbols. So our equation of f inverse was 6 over x plus 2. We're going to plug in 2 for x. So we're going to get, I'm going to do this. I'm going to get 6 over 2 plus 2. Well, 6 over 2 is 3, and 3 plus 2 is 5. Now this says plug 5 into f. That's the original function. The original function was 6 over x minus 2. So 6 over 5 minus 2, which is 6 over 3, which is 2. Now I'm going to go back and I'm going to do this again. But I'm going to start by plugging 2 into the original function. The original function is 6 over x minus 2. So I'm going to get 6 over 0. Wait a second. 6 divided by 0? I can't do that. Remember that 6 divided by 0 is not 0. It really isn't 0. Check it on your calculator. The calculator will not say the answer is 0. We call this undefined. Keep that in the back of your head because it's going to make your lives a lot easier in pre-calculus. So we know that the value 2 is not in the domain of f because when you plug it in, it does not exist. And that is inverse relations and functions.